who will be speaking about how unique is your onion. So she received her PhD from Drexel University and is currently working in Rachel's lab. And she's beginning a postdoc at the KU Leuven. So looking forward to her talk.
I see. No worries, I think I can see over it. Okay. Thanks. There we go. So I am Rebekah Overdorf. I work right now with Rachel at Drexel, but I'm kind of in between right now. Next month I'll be working over at KU Leuven. I'm presenting on some work that I've done with some collaborators there, Mark Juarez, Gunessa Carr, and Claudia Diaz, as well as Rachel. So let's first step back and talk about what Tor is. Tor is an anonymity system, the largest of its kind, that allows a user to access any web page without the web page knowing where they're coming from. It also protects against an attacker being able to see any one point on this connection. So it sends your request for which website you want to go through 3 different relays encrypted along the way so that you're protected at any point if you have an adversary looking at any point on the line, in theory. We're going to talk about one type of attack on this network, although there are many, where our attacker can access just this point here. That is the point between you and the first relay on Tor. And we're really interested in this attacker because it's the kind of attacker that Tor explicitly tries to protect against. That is, it can be deployed with low resources and just by looking at one spot on this network. So here we have a user who is accessing a web page, and our attacker can see the connection between them and their ISP, or it could be their ISP, for example. So first, how does this attack work? As I said, we have our attacker who sees this line that I've highlighted here, and he visits a bunch of websites that he suspects his victim is going to visit. And he looks at what the packets, that is the incoming and outgoing packets on that wire for the request, look like when he visits each of these individual web pages. And he builds a database of these. And he can see things and kind of make features from this based on the number of packets that are sent, the average packet size, the percentage of packets that are incoming versus outgoing, any timing type features for how quickly things are coming in and out, etc. And so later, when our victim comes back and accesses a web page, our attacker's still there looking at the wire, and the attacker says, I've seen this before, some fancy machine learning in the middle. I can say that this person is going to the Mayo Clinic website. We're going to focus specifically on what are called Tor hidden services. So hidden services are services that by design can only be accessed through the Tor network. Many of these services choose to be hidden services or hidden from the normal web because they host sensitive content. So WikiLeaks is a great example of this. Not only does the website not know where the user is, but the user or anyone accessing them can't determine where they are. But this also makes them natural targets for website fingerprinting attacks. And unlike the regular web, there are only a few thousand of these sites at most. Unfortunately for them, but fortunately for us as researchers, this puts us in a nice little closed world model where instead of saying, are they visiting any of these 50 websites or something else, we can just say, we have a couple thousand, we're going to collect them all. Are they accessing any of them? Which makes our job a little easier, but unfortunately makes it a little easier to do this type of attack. So we collected 70 visits to each website over a couple of weeks to 482 different hidden service sites over Tor. And you might be wondering how we can figure out if a user is going to Tor or not as an attacker. So you're an attacker, all you see is this traffic going back and forth, but fortunately someone else discovered that yes, you can figure out if a user is going to a hidden service over Tor or just visiting a different website over Tor. So we're going to look at 3 current state-of-the-art attacks. The first is KNN. KNN uses a KNN classifier, which is just determining what the closest in end space the vector is to a different vector, to the vector that the attacker has access to. The next is K-fingerprinting, which is kind of this neat idea where you take your attack vector of all of the different features and you build trees out of them and then use the leaves of the trees as a fingerprint and put them into KNN and tells you which one is closest to it. The last one is Kumul, which takes into consideration this like timing as well as the size of the packet by interpolating over all of the points as the packets come in and how many packets have come in so far, as well as looking at just general size features and how big or small things are, and then it throws it at a support vector machine, and it gets great results. So these are the results for our data set using these 3 state-of-the-art attacks right now. We get the best results, as I said, with the Kumul classifier, and the other 2 still perform pretty well in the hidden service space. Again, our N here for the number of classes we have is 480 some, so the fact that we're getting 80% accuracy with a 400 some, almost 500 classes is pretty high. So 80% of the time we can distinguish these landing pages for the hidden service websites. But we take all of these and we're going to combine them into an ensemble classifier that we've made. The goal here really isn't just to make a new method that outperforms the 3 that we already have, but instead to kind of understand on the whole how they all, how website fingerprinting attacks do generally. So the combination of these 3 attacks. We look at a couple different ways to make the ensemble classifier here. The first is just, so here with the 3 methods, we feed it the packets, and it's going to give us kind of the first, second, third, fourth choices with the probabilities that it's each one of these. So the easiest and quickest way to do it is just take the one with the highest probability, so here we would pick KNN. The next one is to take straight voting. So we would say take the results that they voted on the most, so here it would be the combination of KFP and Kumul, both think that they're going to website A, so it's A. The one we found actually works best is the P1, P2 diff ensemble, which is when you take the highest minus the second highest probabilities and see what's the biggest. So it's the one that's the most confident in its right answer and the least confident in the rest of them. And so for this case, again, we would choose website A for KFP. And we do outperform Kumul just a little bit. Again, we're really just looking at how all these methods act in general and how the website fingerprinting attacks work generally on these types of websites. But this is where most website fingerprinting work kind of stops. It says we made this attack, maybe we made a defense against it, but and we do a little better than the last ones, and so we're good. But our goal here isn't just to see how well these attacks work in general. That's pretty well studied. If you're a hidden service provider, you don't really care how well KFP works in general on the web. You care about if KFP can identify your hidden service from someone trying to access it. And so what we're going to look at are the misclassifications that happen in these websites. That is, the websites that are safe from this type of attack. And we want to know, are certain web pages or certain hidden services more susceptible to website fingerprinting attacks than others? And if so, what makes them so? And is it consistent? To do this, we define a fingerprintability score. So this is just a measure of how easily a website or a hidden service is identified by this ensemble method we've created. And we use the F1 score from the ensemble classifier. F1 score balances precision and recall versus just using straight accuracy. So as a hidden service, this tells you not only how often you're identified by the classifier, but also how often other people are identified as you, which in a lot of cases is just as important to you. If there's some malicious site that is doing something bad, you do not want that site to be classified as you if you're a fairly normal site doing normal things. So it's just as important to you. So we'll start with the nice pictures. This is what we call a confusion graph for the Kumul classifier. So each node in this graph is a web page or a hidden service, and each edge in the graph is misclassification. So we have like the big orange dot there on the right side has a lot of sites that either it is misclassified a lot or a lot of sites are misclassified as it. And we're going to take a couple things to observe from this graph in general. First, we see all these ellipses. So these ellipses tell us that we have a lot of sites that are just confused with another site back and forth. So like the purple one in the top, your right, we have one hidden service that's consistently misclassified as a different one, and vice versa. So there are two sites that are very similar that are getting mixed up, and we see a lot of these ellipses here. The next thing to look at is these clusters. Here we have a bunch of different sites that are being misclassified as other sites. So these are sites that are fairly safe from classification, meaning that they're hidden pretty well through this method. So now that we've looked a little bit at how Kumul fails, let's see how all of these methods fail together. This is a Venn diagram of how each of the classifiers misclassifies their sites. So you can think of in the Kumul graph, all of the nodes in that graph are contained in the Kumul circle over there, with the edges there. So we see that 31% of sites about are hidden from all the attacks. And that the rest of them are only hidden from one of the attacks or from two of the attacks. We can also look at this and see which sites are misclassified in the same way. That is, if we had one of these big graphs that I had from the beginning for each of the methods, instead of just for Kumul, we would have, in the last graph, we saw the nodes that were in common, but here we would also see which of the edges are in common. How is one misclassified as the other in the same way? So A to B, A is misclassified as B in Kumul. Is A misclassified as C, or is it misclassified as B for K and N? And we find that only 2% of our misclassifications happen in this way. So all of these attacks, even though 31% are consistently misclassified by all of them, only 2% of them fail in different ways. So now we see kind of why they fail, how they fail. Let's talk about why they fail. We find that there are two important predictors for failure here. The first is the size of the site, and we also see that a lot of the features that are used by these classifiers are proxies for size. And the second is staticness. That is, features don't change between visits, or if they do change between visits, they're much more likely to be hidden. For the purpose of the time and for this talk, I'm just going to focus mostly on size. I have a paper at CCS if you want to read more about static and dynamism. So here we have again, all misclassifications. On the x-axis, we have the size of the site itself, and on the y-axis, we have the size of the site that it was misclassified as. So the size that the classifier thinks that the site is, so how it got it wrong. And we see that we have this really nice red line right up the middle, which tells us that sites that are misclassified by our ensemble classifier are classified as a site of the same size as they are. So now that we know this, up to this point, we've only looked at the misclassifications, but that is the sites that are well hidden. But there are other sites that are, most of our sites in our data set are pretty consistently classified correctly. So let's look at those a little more. Our y-axis here is fingerprintability. Recall that that's a measure of how easily or often a website is fingerprinted. So a higher fingerprintability means that our site is identified super consistently, and a lower fingerprintability means that it's really well hidden from this type of attack. And what we can, this is plotted against the incoming packet size. So the smaller sites are closer to me, and the larger sites are farther away from me up here. And we see that no large sites are hidden from this attack. But we also see that a ton of small sites are hidden from this attack, comparatively. So no big ones, but a lot of little ones. And so if you want to be safe from a hidden service attack, step one, don't be one of these big sites over here. Make yourself a smaller site. But even in this case, not all of the small sites are hidden from this attack, so it's not the whole story. You also need to be have a little bit of dynamism between visits, so that your web page is changing constantly between visits. But we've just been looking at these super low level trace features. And again, if you're a hidden service designer, sure, you're interested in kind of what your trace looks like, but you don't make web traces when you make a web page. You make websites. you make the HTML. So while our attacker has access to these trace features like the number of packets, the average packet size, and the percentage of packets that are incoming and outgoing, our web developer over there has access to some high-level features. So like the number of resources, the number of fonts and what they are, the number of scripts that they're used, etc. We use screenshot size as a nice proxy for the number of resources as well, because it gets across things like how many images there are very nicely. And so we want to know, as a hidden service, again, can we determine what characteristics of our web page, or hidden service web pages in general, are affecting their fingerprintability? And we do this through a meta-learner. And since this is a machine learning session, we're going to throw more machine learning at this problem. So here, we're the attacker. We have access to this huge database of web pages that we've come up with, and we can figure out how fingerprintable they are based on how well my classifier performs on them. But our web designer has access to these high-level features that she made, and also her fingerprintability score. So again, we kind of have two different levels of features here. The fingerprintability score we can pull from this trace level feature, and these high-level features that we get from the web developer herself. And we train our classifier on these site-level features using the fingerprintability score as the label. And our goal here really isn't to predict fingerprintability, although it looks like it. The goal is to analyze how the classifier is making decisions and analyze which features are important to these decisions. So for that reason, we use a random forest because it's very interpretable, very nice for these things. And we come up with kind of a feature ranking for different sets of our data set. So we have using all sites, just the smallest sites, and then using the largest sites. We find that when we look at all the sites or the largest 10% of sites, we get a lot of these size features being very predictive. Screenshot size, obviously, for all sites, but then we have things like the HTTP download size, the screenshot size coming in for the largest 10% of sites. And then we start getting these standard deviation features for the smallest 10% of sites, meaning that these small sites are not only small to hide themselves, but they're also dynamic in nature. So the standard deviation is we visit a site 70 times. How much does the screenshot size change between each visit? I'll talk briefly about one interesting site in our data set, which is SecureDrop. If you're not familiar with SecureDrop, it's a whistleblower submission system. It allows journalists and media to publish, to protect the identities of their sources, to be able to send them data and info and things like this. The SecureDrop site in our data set had a fingerprintability score of 99%. It is not hidden from this type of attack. We have some other interesting pieces in our data set as well, but it's important to know as a hidden service, if you're a hidden service like SecureDrop or like WikiLeaks or whatever one you want to pick, to know how your site is going to be protected against this type of attack versus just knowing how that this is a threat in general. And so there are multiple SecureDrop sites, but they don't offer, that are run by different agencies, but they don't offer much protection in general. So in conclusion, website fingerprinting attacks are successful against Tor hidden services, as they are on the web in general. And certain websites are more susceptible to these attacks than others are. And the reason for that is because of their size as well as how dynamic they are between visits. So I have a couple minutes for questions, which is awesome. And I'll also leave my contact information along with the contact information of my co-authors if anyone has some questions otherwise. Thanks.
So we have time for one question.
Thanks. Obviously this is a very serious issue, especially in the press area. Do you work with any of the Freedom of the Press Foundation or any of those organizations to help them harden or further hide their SecureDrop sites or things like that, or do you have plans to do so?
Yeah, so, sorry. We have been working a little with SecureDrop in how to kind of plan against this type of attack. So yeah, we're definitely in contact with sites like this to try to help with this, as well as the Tor project to see how to implement this defense, not on the server side, but on the client side as well.
Okay, so unfortunately we are out of time. So let's thank Rebekah again for the great talk. Really interesting stuff. Our next speaker is Carrie Gates, who will